So it's good that we have one more to do because it'll kind of remind us if there's our notes out. So here they come. Wait. We have one more problem here. So we are in 2.6, problem number 7. Okay, so let's kind of wrap our heads around what do we need here, where it says label all. What are some of the things we'll be looking for in our picture?
Vertical asymptotes, horizontal asymptotes, holes.
Okay, now, this horizontal asymptote thing, I need to understand, another name for these is end behavior asymptotes. They aren't always horizontal. So in your homework, you will have a problem like this one. It will have an end behavior asymptote, but it won't be horizontal. Okay, so I want to just recap that and make sure everybody's with me. When I'm doing these rational problems, I can have a situation where I have 2x squared over 3x squared. When I have that situation, that asymptote's going to be horizontal. It's going to be at y equals 2/3, right? If by chance I have 2x over 3x squared, that asymptote is also horizontal, but it is at 0. If I have this, then my asymptote is not going to be horizontal. And in fact, back when we did this in chapter 1, you literally wrote no horizontal asymptote. But there is an asymptote. It's a slant. And remember we were talking about that? That happens when the top power is bigger than the bottom, which is the situation we have here. So I know on the homework paper, and a couple of you have already done it, turned it in. I know on the homework paper it says horizontal asymptote. Please put in the word end behavior asymptote. Because sometimes they are horizontal, but they don't have to be horizontal. Okay? All right. So, we need that. What else do we need? What else is going to go in our picture? Our 2 asymptotes and then what? Any holes that we might have?
X and Y.
And then the x-intercept and the y-intercept, right? All right, so here we go. Here's our problem. We're going to draw a picture of it, and we're going to include all of that stuff in our picture. So how do we start? Factor. Factor. Why are we going to factor first? What do we have to factor for? To see if there's any holes. That's the only way you'll know, right? Is if you factor and cancel. So, here I go. I'm going to factor. And how does the top factor? -1 plus 3. Okay, great. I factor. But I'm not going to have any holes. So that's going to be nice, which is fine. That's fine. All right, can you tell me what I do have now?
Vertical asymptote.
Where's my vertical asymptote?
-2.
X equals -2. So make sure, guys, when you write that down and when you label it, it's X equals -2. That vertical, or an asymptote is an equation. So X equals -2. All right, what else do I have?
You have 2 x-intercepts?
I have 2 x-intercepts, very good. Where are they? They come from right here, guys. Right here. So I have one at 1, and I have one at -3. Perfect. Those are my x-intercepts. You can have more than one x-intercept. Oh, goodness gracious. Think about the pictures remember these things we just sketched? Look at all those x-intercepts, right? Yeah, you can have a lot of them. Y-intercept, you're only gonna have one. You're only gonna cross the y-axis once. And how do we find where that is? Let x be 0. So go back to my equation. I can either go here or here, whatever's easiest for you. I like to go here. If all the x's are 0, then don't I have negative 3/2? Or negative 1.5? Did everybody follow that? Well, that about covers everything except my end behavior asymptote, right? Who remembers how we find that? Who
You have
remembers how we
to
find
do the synthesis, or the division.
We're gonna do the division, that's exactly right. So, just refresh your memory when it says label all, this is the stuff we're talking about labeling. I'm gonna erase it now because in order to find my slant asymptote, my end behavior asymptote, I'm gonna do a division. 1, 2, -3, that's these numbers right here. And I'm dividing by this, so what's gonna go in the box? -2. 1 comes straight down, so -2, -3, thank you. Alright, who remembers, okay, what do I do with this now that I've got it?
It's like x plus 0 technically such as x, right?
So, this is the remainder, and we ignore that, okay? This, what's left, remember, like all division, you decrease the power by 1. So doesn't that say, like Jake said, x plus 0? Or just plain x if you prefer? Y equals that is my asymptote. That is my slant asymptote, my end behavior asymptote. So I'm gonna go ahead and sketch that in. That's the line. It goes through the origin and has a slope of 1. We've called it the identity, right? And now I gotta figure out what my picture looks like. So let's see. See these 2 points right here? And they're gonna be connected. And I'm gonna follow my asymptote. So as you're connecting your dots, you're following your asymptote. So this piece right here, look at it, does that make sense to you? It's framed inside those asymptotes. Now there's always another half to the picture. Where is it?
It's like,
See that point right there? So it's gonna be framed by these asymptotes right here. So it's gonna look like that. Now that's the last example we have of that. So we'll, after we finish 7, which is gonna take us a while, if we finish it, we'll come back and do a review on these, because we'll be having a quiz over 2.6 and 2.7. But before I erase this, is there any phase of that problem that you're still not sure where something came from? Katie,
So when do you know when it's synthetic division?
can somebody help her out?
and you don't find a horizontal asymptote.
Which happens in one circumstance.
When the power is bigger on the top?
Exactly, exactly.
For this one, how we did it for everyone, that's what this is on.
What do you mean?
Like for this one, it was like,
Well, that was a whole different picture because that had 2 vertical asymptotes. So there were 3 chunks of graph that I had to do, and so I had to figure out what was happening in each chunk. When there's only 1 vertical asymptote, you've got a chunk on the right, which was that, and then you had a chunk on the left, which was that. Okay? All right, let's look at 2.7 now. 2.7, okay, so 2.6 is about taking things like this and graphing them. 2.7 is about solving equations with things like this in them. So we call it solving rational equations. We've done it before, probably really good at it. Let's look at the first one. What's your thought? If you found this just laying out the hallway and you had to solve it, what would you do? Multiply by x. The purpose of that would be to get rid of the fraction, right?
Yeah.
So if we times everything by x, I have this, the biggest mistake, honestly, that happens with these is kids will put 3x. No, if you're timesing by x, the x is gone, right? There's no x for this guy. All right, now what?
You could
Set it equal to
0.
0. Isn't this a quadratic equation?
Yes. And you could
So
factor.
we like to get our quadratics equal to 0. And when I do that, I'm gonna put that 4x kind of in the middle of the problem where it belongs. Now what do?
Factor.
You can factor, or, I got this problem out of the book, so it's rigged. If I'm making it up, it probably isn't gonna factor, which means you would use the quadratic formula. Which you could use anyway if you wanted to, but this one factors easily. So I got 3 or 1. You okay with that? Now, one thing I wanna remind you of, whenever you have an x in the denominator of your problem, you have the potential of what are known as excluded values. So in this problem, right from the very beginning, I can tell that whatever answer I get, it can't be 0. Would you agree with that?
Yes.
So if I solved it and got 0 as one of my answers, I would have to throw that one out. Be on the lookout for extraneous roots, excluded values. All right, next. All right, what do you want to do with this one?
Multiply by x minus 4.
Multiply by x minus 4. Now, there are other ways to do it, so I don't want anybody to get discouraged if you have a different thought. That is a great way to do it. Same reasoning as over here, we want to get rid of the fraction. So x minus 4 minus 1 equals 0. Because when you times by x minus 4, 0 times anything is still 0, right?
How do you get minus
Is
one?
that plus 1?
I have no idea. I just made that up. It's plus 1. Yeah, 8. Okay, now what?
Do it. I don't know what.
Distribute?
Yeah.
There's our quadratic that doesn't factor. So x equals negative b. By the way, you could complete the square on this one if you wanted to. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So 4 plus or minus the square root of 12. And the square root of 12 is 2 root 3. And now everything's divisible by 2. This is the problem that never ends. X equals 2 plus or minus root 3.
Yes, that's correct.
What is my excluded value for this problem? 4. Do you see that? That if you couldn't, if you did all this work and came up with x equals 4, you'd have to throw it out. Because x can't equal 4 in this problem. Oh boy.
Oh, don't say that in the board.
Well, just look at this next one. I don't know.
Don't scare us.
I'm not scaring you.
You did.
I'm not scaring you. You're not afraid. This is not too bad. It just looks bad. Yeah. So now, wait a second, does everybody catch I factored that?
Oh, yeah.
Okay, so we always wanna factor. If things factor, always factor them. It'll never hurt, sometimes it helps. Now, that is a big equation and we need to solve it. So what are your thoughts, Jake?
Can we want, like, the two one on the left side, we multiply it by the opposite, so we can like cross out the bottom?
Oh, you mean like kind of the conjugate idea?
Kind of.
That won't work because x minus 3 and x plus 3 don't cancel. That only works with i's.
Wait,
Go ahead.
I meant like, so you know like on the bottom, if you get all those equations that have an x minus 3 and x minus 1, that's what I was trying to say.
Okay, now I got you. Now I got what you mean. Okay, so this one would need to have an x minus 3 if it were going to match this one, is what Jake is saying. This one would need an x minus 1 if it were going to match that one. So one way to do this problem, not the only way, but one way to do this problem is to make all the denominators the same. Notice that when I multiply, when I put an x minus 3 in the bottom, I had to also put it on the top. What happens, or what are you allowed to do once all the denominators are the same? Get rid of them. They're gone. You can totally ignore them. So at this point, all we have left is the numerators. These are all gone. The beauty of making a match is you can get rid of them. So we'll distribute here. Everybody still with me? And collect like terms. And get a 0. Now keep an eye on my arithmetic. We know I already made a mistake somewhere, so. Did I do okay with that?
Wouldn't it be negative?
Yeah, it's like 9 to 1.
Yeah.
Oh my gosh.
It's alright, this for it. It happens.
I'm
Yeah,
just-
exactly.
You know what? I think it's setting in. I think the old,
This for it. You will never get old, ever. You have eternal life.
I appreciate that. That ship has sailed, I'm already there. Okay, all right, so this lecture looks better to me because this one does factor. Now, you don't have to factor it. You can always use the formula, but this one does factor now that you fixed it and corrected me. It does, so, all right, just stop. I think I factored it right.
You did.
Thank you. So that means my answers are 3 or negative 1/2. Uh-huh. Those extraneous radar going up. Beep, 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 beep. X cannot be 3 and X cannot be 1. So if we get either one of those answers, we have to throw it out. So very good, Kara. The only answer to the problem is negative 1/2.
So what if like the only answer was 3 and there wasn't like 1/2? Would there just be like no answer?
solution.
Okay.
Means you would have done all that work and no answer. Because it's possible for both of them to get thrown out.
Okay.
All right, here we go. Next, looks like the same thing. Oh, that's not an equals, that's a plus. I'm gonna go ahead and factor that denominator. All right, and go ahead, get started. See how far you can get with this guy. Brenda, this is what you're talking about here. Because the two things x cannot be would be 0 and -2. And we just went through and did all that work, and those are the two that we got. So this problem has no solution. We gotta be on the lookout for those extraneous roots. Excluded values. Denominators can never, ever be 0. Alright. Everybody okay with that? That seemed pretty easy for you, good for you, easier for you than me, actually. Here we go, number 5. 5 and 6 are examples of what we call work problems. Now, they're not work problems like you do in physics. In physics, you have the physical concept of work. These problems are like Susie and Billy are both doing a job, and they can do it alone, they can do it together. They're working on a task. The general formula, you may have done this differently before, but the general formula I like to use for these problems is 1 over the first guy's time alone plus 1 over the second guy's time alone will be 1 over their time together. So think about it like this. If Billy takes 4 hours to do the job, then in an hour he can do 1/4 of the job. And if Susie takes 8 hours to do the job, then in an hour she can do 1/8 of the job. So if they're both in here working, let's say they're painting the walls, they're both in here working, after that 1 hour, we have 1/4 of it done and 1/8 of it done. That's what's going on in this problem, okay? So here we go. Jessica can do it in 5 hours, 1 over 5. Brenda takes 6 hours, 1 over 6. How long will it take them together? 1 over x. It's real easy. Does that make sense to you? I mean, if this is the setup we're using, that would be our equation, right? So now what are we gonna do? Multiply the whole thing by 30x. Now, if we do that, if we multiply the whole thing by 30x, then this will be 6x. This will be 5x, and that'll be 30. Now, that isn't exactly how we did our last problems, but that will work. This will absolutely work. 30x is the common denominator. We just didn't physically get the common denominator, we kind of cleared it out. So 11x equals 30, and the answer is whatever 30/11 hours is. That's how long it'll take them. Not quite 3 hours to do the job together. Oh, that seems easy. Here we go, number 6. A drain is left open as a pool is filling. Hose X can fill it in 10 hours. Here's hose X. Hose Y can fill it in 4 hours. And the drain is open. If both hoses are running in and the drain is open, it takes 15 hours to fill the pool. So the end result is 15 hours. I got everything open, hoses in, hoses out, takes 15 hours. How long does it take the drain to empty the pool? How's that gonna work in this equation? Would it be plus 1 over x? Now what's wrong with that? It would be minus, because aren't the hoses going in, so they're working together, but the drain is going against that? Does that make sense to you? So that's gonna be minus 1 over x. Okay, so everybody's okay with that setup? Yeah, this guy going in, this guy going in, this guy going out. And altogether, it takes 15 hours for all that to happen. All right, what am I gonna multiply by this time? 60x would definitely work. So that'll leave me with 6x, 15x, and 4x. Double check all that. That's got me like panicked now, like another dumb mistake. I got 60/17 hours.
That's what I got.
That's what you got? Good. And what does that stand for? That's how long it would take the drain to empty the pool. All by itself. We have a full pool, full plug, that's how long it's gonna take to empty. Everybody good? All right, number 7. All right, breaking even. It's on sports apparel. X is the number of hats each week. Is first the average cost of producing one hat of a function of X. You know what, let's cross off A, we don't need to do A. We wanna solve algebraically to find the number of golf hats that must be sold each week to make a profit. Okay, so we're doing B. We're gonna find the number of hats we have to sell to make a profit. What's profit? Come on, econ students, what's profit?
Revenue minus whatever you make.
So it's like income minus expenses. That'll be our profit. Would you agree with that? Kind of general thing?
Yeah.
All right, what's our income? How much money are we making? We're selling hats. How much are we bringing in? Not our profit, but how much are we bringing in? $2.75 X. Every hat I sell, my income is $2.75. Right? Now, what are my expenses?
12x.
So 212x, that's part of my expenses, because to make a hat, it cost me $2.12. What's the other part of my expenses? 3,000. What's the 3,000? Does anybody know what we mean by overhead?
Or is it like the labor put into it, or what?
It's like, yeah, it's like the lights, the light bill, the water bill, the taxes on the building, the insurance. That's what it is. It's all the other things that go into making a hat. Right? Okay, and what do we want? That's gonna equal our profit. What do we want about our profit? Okay, so we wanna make a profit. What does that mean about these two things? If we wanna make a profit, they have to, this one has to be bigger than that one? So can I just do this? Forget the equals part. My income has to be bigger than my expense?
Yeah.
Does that make sense to you? Alright, let's solve it. That should be pretty easy. I should be using a calculator, given my luck today, but is that 63x? And divided by 3,000 divided by that. We have to make more than 4,761 hats, or greater than or equal to 4,762 hats. has either one of those answers would be okay. Is that okay? Last one. How many golf hats must be sold to make a profit of $1,000?
Well, is it the same?
Can we go back to here? Go ahead and make that a minus. And then it has to be, does it say at least, or make a profit of 1,000? Let that equal 1,000? Will that work? Take my income minus my expenses, and I need that to be 1,000? So, that minus that. So I'm gonna come up with actually 6350 hats. Can't have fractional hats, so I'll have to round that up. 6350 hats to make a profit of 1,000. Everybody okay so far? Okay, we're gonna stop there because the period's about over. According to some schedule on that, which I think is right. All right, so 2/6 is due Thursday. We will finish 2/7 next